In this video, we're going to talk about Stokes Theorem and its proof. Before we go and talk about the Stokes Theorem, I'd like to mention that this is actually connected to Green's theorem, and you can view the Stokes Theorem as a sort of generalization of Green's theorem and without changing its dimension. But you can also look at this Stokes Theorem and in the middle of this, in the path to the divergence theorem. So you see three things are very interestingly related. So once you know the Stokes theorem, you can view this as Green's theorem generalized to Stokes theorem, and then the relationship between these two, Green's theorem and Stokes theorem, can view it as a, the same thing is happening through the Stokes theorem to Green's theorem. So where it goes like that and from goes like that. So first, let's see how this one is viewed as a generalization to the Green's theorem. First, the setup. Setup is, well, here it is. We start with a nice oriented curve and another condition about the surface that has this C as a boundary. So here it's a closed curve. That's something that I have to set that earlier. Closed curve, and this in between this closed curve there's a surface such that its edges happen to be this curve that started with. And curve has orientation, and if you look at the surface, it has some both sides. So which way it's whatever it is pointing, that is called orientation. Once you have this curve is oriented this way, again, looking at the interior to the left side, if that's intuitively okay. Again, left side is the orientation of that. And once you have that side on the left and using this right-hand rule, and wherever thumb is pointing is upward relative to the curve orientation. So both small class of examples that using right hand and waving my hands like that kind of makes sense, but the formal definition may require a little bit of setup. But let's use our intuition and say we understand this. To make this proof and straightforward and clean and just to deliver the idea behind the proof, another nice condition we're putting on the surface is that such that this surface is sitting on there, if you project it down to xy, if you look at over xy plane, this whole thing must be the graph of a function, two-variable function. And then the treatment is going to be, straightforward. Still is going to be complicated enough, and you're going to see some calculation that's interesting enough. So that's the setup. In this case, the line integral, that's a Green's theorem. Right? Green's theorem is about the line integral on xy plane and how that is connected to the double integral in that xy plane. So here is a line integral in xyz space, which is similarly defined, and there is this integral, which is called the surface integral, not double integral. Double integral is triple integral is limited to so-called the flat surface, xy plane or xyz. This surface here is sitting inside the xyz space and curved around. So for that one, we don't say it's double integral, we say the surface integral. Hope you have the definition of a surface integral. You have learned that. All right, here's a statement. In that setup, how is this, does it look, why does it look like a Green's theorem? So here it is. So here's a statement. If you have line integral going around like this, and there is a vector field defined on the space, and this line integral becomes like a curved double integral, so surface integral. So we have this surface that has this curve as a boundary. Sorry about the interruption. Let me do that again. Here's a surface integral. So there's a surface S with the orientation. And there's a new vector field called the curl, which is viewed as a generalization of the Green's theorem. If remember how I presented Green's theorem, we call it a scalar curl, and it is dotted against the normal vector pointing to the direction of orientation. That's where the orientation is used. And what is this curl? And curl is defined like this. If f is given by these components, p, q, r, x component, y component, z component of the vector field, and the curl of this vector field is defined like this. Ry with respect to partial, with respect to y, with respect to z, and so on. And this is something we remember, qx minus py. So let's see how this one is viewed as a generalization. If the curve is on the ground on this xy plane, and the surface happened to be flat, and this dy, this vector field here, only has a p and q part and does not have r part in there, right? Because all the vector field down there in the Green's theorem is in xy plane. So it does not have r components and it does not have z components. So whenever you're differentiating r, that's going to be 0. Whenever you're differentiating q with respect to z, that doesn't have any z in it because q is p and q are all involving x and y. That's going to be 0. Again, anything with respect to z is going to be 0. R is 0. So this is viewed as a 0 and 0. And then it only leaves qx minus py, which was a scalar curl. We have seen that before. And because S is a flat surface on the ground, and this normal vector, which is orientation vector to the surface, is going to be always pointing upward 0, 0, 1. So that 0, 0, 1 dotted to the curl will pick up this qx minus py. So that's using that statement, we retrieve the Green's theorem is one way to view why this one, Stokes theorem, is the generalization of Green's theorem. Kind of same thing, the integral phenomenon is lifted up into higher dimensional space, but it remains at the same curve one dimension and surface, but it's curved around. Getting interesting in there. So that's the theorem. And just like the corollary and consequences we had from the Green's theorem, it has the same phenomenon in there, but it all happening in x, y, z space. This is one of the examples we had before. If the vector field in the space has x component only depends on x, y component only depends on y, z component only depends on z, then what is a curl? Okay, so you have to actually calculate that carefully. Ry, and r is a z component, and it only has z in that, so that's going to be 0. Q has only y component, so with respect to z. P has only x component, nothing there. R, z component, nothing there. Qy, py, everything is 0, so the curl is 0. So you see this line integral in the space is going to be 0 because of this right-hand side, because the curl is 0. That's why this one's 0. I forgot why that one's 0. So once you have a line integral 0 over this closed loop, the consequence of that is if you start and ending at common beginning and terminal point, however you go to that from the beginning to that end, the line integral will be 0 to make this the vector field conservative, I think, as long as the curl is 0. Right? So that's one of the things that we discussed in xy plane. And the most important example of this vector field whose curl is 0 was a gradient vector field for 2 variable. Let's see if that is true for 3 variable as well. So you start with a scalar function f, to mention that here. F here is a scalar function, like a temperature. If you pick any x, y, z points in the space, f spits out a scalar. And this is a gradient vector, f differentiated x, differentiated for y, and differentiated for z. And let's go ahead and calculate the curl f. I think I forgot to mention how we got this one there. So I apologize. And then we're going to just calculate this one first and go back in there and understand how this came about. Right, here it is. I don't know if this is going to make sense or not, but I think following principles, think about what happened to P and Q. When you're doing P and Q, the scalar curl was swapping these two and keeping the order of xy for the differentiation order, so qx minus py. So, for example, like that, for the first component, it is about the other two components. So this is from left to right. So if you start from the third one, go to the first one, if you go around the loop, so this one is the first one and that's the second one. So again, the first spot, we're going to do the second and third, and you have to swap it around. So that one goes to the first slot, FC, differentiated with respect to y, the second slot. So that one goes to the second slot in there, and differentiated with respect to z. And that's what you see there. Okay? So let's see, for the second one, if you're missing the second one there, next one is FC and FX. Okay? So let's do that in this extra space I prepared there. Let's see, I don't want to block it, anything there. So what we're looking at here is FZ and FX. That's a Z slot and then that's X slot. And what we're doing with that original Green's theorem P and Q is that you swap this one FX and you would differentiate with respect to Z and swap that one in there, differentiate with respect to X. That's the slot, and then you subtract it. I hope you see that's the same thing we're doing in P and Q. That was X slot and Y slot. Swap it around, but still differentiated for X and Y in the place and to do the minus there. So that's appearing in the second part right there. Now for the third part, you have to go around like this, just keeping the order, in the consistent. If you're in that place, you go to fx and fyz, fx and fy, and this is x slot and that's y slot. You swap this one there, differentiate it with respect to x because that's in the x slot. That one goes there. This is the y slot with respect to y, like that. Okay. So that agreed with that one, right? So let's go ahead and calculate this one first, and then go back to that original part there, and also explain the more standard way of explaining using the matrix multiplication. So now, because it's something called the Clairaut's theorem, we mentioned that in Green's theorem too. So that's fzy and fyz are going to be equal to each other as long as the second partials are continuous. fxz, fzux, fyx, fxy, they're all 0. Therefore, it has a trivial kernel. It is a trivial kernel because of the Stokes theorem. The whole thing is 0. Because of that, you can see the line integral, again, is going to be conservative as long as your vector field happens to be gradient vector field, right? So before we move on to the next part, which I think is a proof, let's go back and here explain that one more time about where those things came from. The way they explain how this formula came about is using this matrix multiplication. That's pretty neat. They usually write it like this: is a gradient. I think it's because of the partial structure cross product with the vector field f. That's how they usually write this curl. So it's that's how they define, I think, denote the curl in there. What is this notation? If it is a vector, and you will write it here and then 3 spot, and that's a second vector, you will write it underneath it, just like I did it over there. And then you cross product, do the cross product to find the third vector that is perpendicular to each other. So similar phenomenon is happening, is mainly because it's associated with the determinant algebra in there. So they usually write this operator. What are we doing with the gradient vector? We look at the scalar function and differentiate it with respect to x. So they write it like this. So more proper notation would be partial x like that, and partial y. So this is the differential operator notation only. And then you write down p and q and r underneath it, following their notation. So again, that's the operator, gradient vector operator. And what you do is a partial with respect to x and y and z and putting in the space. So if these are really numbers and the cross product will be for the first component, you eliminate the first column and you do this 2 by 2 matrix calculation, which is if you multiply these two, then it's not really multiplying. It is like differentiate with respect to y and differentiate that. So if you kind of put those together, and if you allow me to say multiplying, putting those together, that's exactly ry in there. So that's neat. So by doing that cross multiplication, we have ry in there. And to this one, it's a qz. So it's a qz is minus ad minus bc, 2 by 2 matrix. So that's how they got that one. And then it's consistent with other ones. The second one is missing. It's not this one because this chain sign is alternating. You have to do this one first. So pz minus rx. Remember alternating sign of the cross product. The third one will be removing this one and this doing this 2 by 2. So you can see that's qx and that's py. So that's how they usually describe it. Gradient cross with the vector field. But it's also consistent with that cross, and you can just do this going around. I don't know which one's faster. Whatever that's more comfortable is more comfortable for you, that you'll be using that, I think. All right. So I think next part is proof. Right. For the convenience, we assume that this surface happened to be the graph of a function in the form z equals x comma y. And the real key observation is that if you look at this integral here, and it's one variable, and if we replace that z with x and y in there, so all the formulas x and y, even that dz part, if we replace that with something in terms of x and y going through this integral, I'm going to write that down later, then it's really two variable. Okay, so algebraically, you can see that everything can be rewritten in terms of two variable. And its geometric interpretation, what we have just accomplished out of that is the following. These curves go around x and y and z. However, this x and z is completely parameterized by this x and y. So this is really just x and y. Everything is just written in terms of x and y. So everything will be projected down to xy plane. Even this curve C is going to be projected down to xy plane, and then it's guaranteed that there will be no overlapping or anything because it came from the graph of a function over each point. There's only one point up there, even though Green's theorem can be applied to that kind of thing, but that's the geometric interpretation. So if we go ahead and replace everything that is involved in this line integral in terms of x and y, and then you can look at this as a line integral on x and y, and it can be interpreted as a projecting down to everything. So let's see a bit more carefully before I claim the next part is the following. So think about all this thing in terms of formula. This integral c that we have written down in here, ending with the dz, all this thing copied down there, and we're going to pass to dt integral. Then p with all the x and y and z in it, all in terms of t. And then there is a dx dt. You have to write it like this, not just a dx, because we entered t variable integral. And this is going to be the same. The q, all the x, y, z replaced in terms of d. And then this is going to change to dy dt. And here's r, x, y, z as well. And here's a dz dt and dt here. The key thing is that this z is already written in terms of x and y, so that this can be rewritten in terms of dx and dt using the chain rules. Let me go ahead and make sure that I don't have, if I have written down this one already in the later part, and then I'm just going to use that one. So I skipped one of those calculation here. Just wanted to just say that one. So I'm just gonna show that calculation here. Think about it like this: if z is composed as in terms of x and y, like that, and then we're differentiating z in terms of with respect to t, that's a typical chain rule. So that means if you look at z as a function of x, y, that, let me write it like this, you first differentiate with respect to x, and then multiply dx dt. That was a one variable, one parameter chain rule, right? Two parameter chain rule is similar. And you differentiate with respect to y first, and then dy dt, not curly partial y partial dt. This is one variable there. So this is a zx and this is a zy, and that's dx dt. So it can be grouped together with the dx and dt in there. Now this is going to be some sort of function. This is a function in terms of function in terms of x and y. There's no z in there. This is a function in terms of x and y, so it coincides. Put them together with a xy function. All the z's replace xy, and then dx dt. Put them together, and then all the thing is going to be, some sort of, got on that right there. That original problem is now going back to the x and y, going around some kind of stuff in there, dx, and I'm going to call p tilde after this. All these things are grouped together, p tilde, and here's a q tilde, dy, and this is only about x and y, and there's a t's involved in doing all that. So as t varies, what is happening to x and y? That's the curve. This is a curve, but we only care about x and y. That's exactly the projection. So if I denote that by c0, that becomes a c0 right there. Okay? So let me show you that what I prepared that in that slide, and I hope that makes sense to you now. So if you look at this first 2 bits, you can have this c in there, but the z is already replaced with x and y. Z there is already replaced in x and y, and there's no x and y in there. So, no z in there, so everything is about x and y. Therefore, this curve is only involving x and y, no z. Therefore, it's the same as a projection. So if you look at just the first 2 part of the term, this is already Green's theorem. Down there, there's a curve C0, and this P and Q, originally 3 variable, now it's putting this formula of Z in there. It's only 2 variables, so that's Green's theorem. And this one we talked about already. You can turn that into Green's theorem as well, as we change that dz using that chain rule. But I think in my next solution, I focus on these first 2 terms. All right. I think I was wrong to say that this chain rule part there, but we eventually use that chain rule. So let me say that Green's theorem part is correct. So that again, this is interpreted as only 2 variable. This one thing I have to be careful is that P is not originally 2 variable. It became the 2 variable. So you have to understand that part. So you cross that. The chain rule makes sense now to me. Then I understand why I wrote there. So I didn't write qx in there. That's the key. Didn't write qx in there and py in there because p is originally 3 variable function. Now you're composing with a z, then differentiated with respect to x. That involves a chain rule to unfold it in here. So this is actually the part that you may easily make a mistake if you just use the p and not specifying what variable is involved. So let me say that again. We're try to apply the Green's theorem to that part. Q is originally 3 variable. With that composition, it became 2 variable. So if you just write Q, and thinking about is now Z is replaced in terms of X and Y, in terms of differentiating, it's different, right? Z was treated as an independent variable before. Now it's not. It is all dependent in X and Y. So that's why I didn't write Q sub X. Get the Q in this expression there, really differentiated with respect to X using the chain rule. 2 variable chain rule in that case. All right, let me explain this part in there. Again, Q has this 2 variable, used to be S and T in there, right? But, x and y and z, they are parameterized by in terms of s and t, in terms of s and t, so on. But that s is x. That let me write it like this: that s is x, and that t is y, and that z is in terms of x and y. So the partial two-variable chain rule goes like this. If you're looking at some stuff, I'm going to use a t here. If you're differentiating t with respect to s, then by the chain rule, you have to differentiate it with respect to this original variable x, and then because x is now two variable in general, so that's why I'm using this, two variable s and t, and here's a dx in there, so we differentiate x with respect to s. The down there is always s in there. And second one, you have to differentiate with respect to the original second variable and have to multiply the derivative of y with respect to this new parameter. And here's a tz third variable and dz here and the ds down there. That's the two variable chain rule practice there. Here, our x is x. Because of that, this is going to be 1. This y does not have s in it. Because of that, that's a 0. And this is truly zs, and here is a zx because of that. So that's t is our q. So qx, that's what you see there, times 1. Qy times 0, that tz will be qz. And the z has a two variable x and y. With respect to s, that will be zx. So the derivative of q with respect to x in that situation is a qx plus qzzx. So that's something that's interesting and something you have to be careful about. So next one is the p. So px and py and the pz appears, but px part is going to be multiplied by 0 because with respect to y, x doesn't have y in it. So that's py. There is no px part in there. Pz multiplied by that z differentiated with respect to the second parameter y. So that's the correct way of differentiating these two things using the Green's theorem. Again, the answer wasn't just qx minus py. Right, down here I collected this qx minus py part nicely because that's the thing that appeared in the Stokes theorem. So we collected nicely there. It's over that xy double integral, not surface integral in this case. And the other term, qzzx and minus pzzy is collected there. Now this part A was coming from this part that I already showed you in the slide over there. Like this, that has a zx and dx and zy dy. That's how that one splits up. So let me show you that. So if you replace everything this in terms of x and y, this dz changes to zx dx and zy dy. Let me show once again, like that one, zx dx, zy dy with the parameter in free independent notation, and r is still there. Again, this r has x and y and this composed thing like that. But once you do that, there's no differentiation going on, so you don't have to do anything like this over here. You just simply replace it. But this dz part is coming from the derivative, so you have to go through this chain rule and derivative. Now with that one, and with a z equals z of xy, everything is in terms of xy, so we can safely change that to c0, bottom there. So even that one, we're going to apply the Green's theorem. This has a dx and zx, and this rzx, you can look at it as a p, and rzy, you can look at it as a q in the Green's theorem and apply the Green's theorem one more time there. That's what we are doing there, and we obtain that from this process that I already explained. Okay, I'm now working on that one, applying Green's theorem one more time to that C0 curve down there, and I'm just going to call everything here B and not copying down, the same thing that I don't do anything about. So this is the function rzx, and if you distribute it as rzy, so rzy come over here crossed, and first slot it differentiated for x. That one rzx come over here, differentiated with respect to y. Now you have to differentiate the product of two functions using the product rule, but also r is originally three variable function, so you can't just write rx when you're differentiating the first factor when you apply the product rule. You have to go through the same chain rule that you have done before. So especially when you're differentiating r with respect to x, you have to be careful. So that's the next part. So here I'm applying the product rule. Product rule to that one, derivative with respect to x. X and y is a variable, so y part doesn't appear. Ry derivative times y with respect to x, that's a 0, but z part is all involved, so rzx. So that's a chain rule, two variable chain rule version 2. zy are not differentiated. zy differentiated with respect to x, so that's zyx. So that's it. That's the result of this part differentiated for x. And the second part, same thing in here with a negative distributed there. This is differentiated with respect to y, so there's no rx part. Ry times 1, then rzy, that's the chain rule. And this second factor zx is differentiated with respect to y. So that's the result. That's this part, Green's theorem applied. Now we have to put them all together, and you will see a lot of cancellation, especially all these rz, zx, zy, those things all turns out. Already recognizing this cancellation, rz, zx, zy, rz, zy, zx, it doesn't require Clairaut's theorem. It's just ABC times BCA. They cancel out. But these two, zyx and zxy, that's a Clairaut's theorem, and they cancel out, leaving only rx and ry with the zx and zy multiplied. So that's what I recognize in here. The whole thing is simplified just to two terms. And this part is putting it back all together. This one is copied in there. That B was what we have gotten out of the first Green's theorem application. So we have all these things together with this double integral down there. Qx minus Py and Qzx, Pzy, hold on. Oh, that's right, they're being collected together, zx and zy. When you're putting this one back into the surface integral from the double integral, this is where the zx and zy is used. So we do not want to see the zx and zy appearing anywhere because we don't see that in the Stokes theorem. So we have to collect them together. So I collect these zx together, zx and zx there, which is qz minus ry. That's what you see in the Stokes theorem. Zy, we have rx there and minus pz, so that's zy. So that's so far what we have. And we're going to put them all together under the same double integral and realize that how do we get this one back to the surface integral. So here's a little cheating going on, and knowing after you try to unfold the result of the Stokes theorem and try to compare it and how this one compares to what we have here, and it boils down to the following. So this qx minus py, and this one is multiplied to that, and that one is multiplied to that. And if you look at the Stokes theorem, this one appears as ry minus qz, not qz minus ry. This one as well. This appeared as a pz minus rx. So we want to put that in that order. Then we're going to put the negative on the zx and zy part. This was already incorrect sign, so I put it in there. Then realize, oh, they're dot products, right? So that's how you're putting it back into surface integral. Right at this stage, I am actually, rather than try to manipulate it back into surface integral, which will be even more cheating there. So I decided to, why don't I just unfold this very meaning of the surface integral to and then compare that with this one. I think that's more reasonable approach. So what is the very meaning of a surface integral like this? Just like line integral, we have to use um, parameterization. When we see a line integral, something like that, it's a compact notation, the recognizing this parameterization independence. But to actually calculate it, you have to parameterize the C. And with that parameter, you go from, because one variable parameter, and then you replace this dr with the dr dt as a vector there, and dt. So we enter this type of more more familiar integral. So the same thing, we have to parameterize this surface S. And because it's a parameterization independent, doesn't matter how you parameterize it, this value will be the same. That's why they write it like this. So you're free to choose any parameterization, but we conveniently assumed that our surface is parameterized nicely over x and y, which is called a modular parameterization. But because of that, our parameterization, as written here, is x and y as a main variable, and third one is a function of x and y. And if it is like a major portion of a sphere, as you can see, you can't do that. You have to split it up. So that's how I do it. Before I was changing the one variable integral because the two free variables involved, and this surface integral switched to a double integral, right? So that makes a connection to our interpretation of earlier calculation, which is a line integral and a double integral. That makes a connection. All you have to do is their definition of curl and our calculation of a cross product of this, which will give you this Rx is tangent to the surface in one direction, Ry is tangent to another if you cross it, and that's going to be our choice of a normal vector there. So that's the normal vector that's being multiplied. And if you use this one and partial and the cross multiply, you get this one, which we will skip. You will probably have done it somewhere else, but it's something you can easily do. So if you do the cross product, you get this one, and that's precisely what is appearing there. So you can see if I replace this Rx cross Ry with their definition of a curl right there, put them together, you see exactly the same thing. Therefore, we show that that is equal to the surface integral. But what was the original this calculation in here? These are all equal, all the way, all equal, right there, all equal. That goes all the way up to that line integral. So this line integral, which is the line integral of a vector field PQR, is equal to this surface integral, right? Already we've seen this as a generalization of Green's theorem. All right. Now we're going to enter in the next video divergence theorem, and then try to put all those three of them together and think about how here's a problem, which way is the best way to calculate that minimizes or makes the computation easier. Thanks.